So these are the learning objectives for Chapter 5. In the first part of the notes, we'll cover these first four objectives. In Part 2, talk about these two objectives, and then Part 3, we'll learn about calculating expected value, and I want to add one more that's not here, and that is working with an example of a discrete probability distribution that is quite common, and it's called the binomial probability distribution. So that's how we'll wrap up this chapter. So first, the definition of a random variable. A random variable is different from a variable you may have studied in algebra, which I call an algebraic variable. A random variable is not quite the same as an algebraic algebraic variable. A variable that has a single numerical value determined by chance for each outcome of a procedure is a random variable. An algebraic variable is a variable that has a value that you can determine by solving an equation. But random variables are a little different from that. So by way of example, let's see if we can explore what a random variable is. This first example deals with tossing a single fair six-sided die. X is a variable that takes on the value 1 if the number showing on the face of the die is odd, and it takes on the value 2 if the number showing on the face of the die is even. So we see that X has a single numerical value. There are two possible values, but X only assumes one of those values, and the value that it takes on is determined by chance, because tossing a die is a chance event. So we see that this X is a random variable. In example 2, we're tossing a coin 3 times, and X will represent the number of times that we see tails up in those 3 tosses. You could think of tossing 3 coins and noting the number of tails. Well, again, in this situation, X is a random variable because it has a single numerical value that's determined by chance for each outcome of the procedure. So every time you toss the coin, you will either have a 3 up or you will not have a 3 up. So you can see that the value of the random variable depends on chance, and it's only one single value at a time. Those first 2 examples are examples of discrete random variables because the variable's values are whole numbers. But the third example is an example of a continuous random variable, and we'll deal with those in the next chapter. But just by way of illustration, if you leave a light bulb on until it burns out, then you can think of the random variable X as the lifetime in hours of the bulb. So this X is a random variable because once the light burns out, then you know the single value that it is, and this is determined by chance. I suppose you could argue how that works exactly, but the lifetime of a bulb is a chance item. And so we see that we have a random variable in this situation as well. Okay, once you know what random variables are, it's time to talk about the way that the random variable is distributed, and that's the probability distribution. A probability distribution is simply a description that gives the probability for each value of the random variable, and it can be expressed in the form of a graph, a table, or a formula. So returning to example 1, where we're tossing a single fair six-sided die, and the variable X takes on the value 1 if the number showing on the face of the die is odd, and it takes on the value 2 if the number showing on the face of the die is even. So we have a random variable. It has a single numerical value, and that value is either 1 or 2, but it only assumes one of those values at a time, so that means it's a single numerical value, and that value is determined by chance because the die is fair and we're just tossing it. So here's how the probability distribution of the random variable appears in a table. The first column gives us the possible values of the random variable, and in this situation the possible values are either 1 or 2. The second column gives us the probability that X will be either of those 2 values, and so we see that the probability that X is equal to 1 is 0.5 because exactly 1/2 of the numbers on the die are what is it, odd. And the probability that x is equal to 2 is 0.5 because exactly 1/2, 0.5, of the numbers on the die are even. And so we see that the total probability here is 1, which is consistent with what we've studied before about probabilities. And so we see that what we have is a theoretically perfect population frequency distribution. That is to say, if you actually sat and tossed a coin many, many times, you probably wouldn't get exactly half heads and exactly half tails. The probability distribution is the theoretically perfect population frequency distribution. And it specifies how the probability is distributed among the different outcomes. For our second example, we tossed a coin 3 times and we let x represent the number of times that tails are up in the 3 tosses. So we see that x is a random variable, and we'll look at the probability distribution of the variable x. We build that by starting from the simple events, or the simple outcomes that we are obtaining when we do this experiment. So if we toss a coin 3 times, the possible things that could happen are we could get 3 heads, 2 heads and then a tail, a head and then a tail and then a head, and so on down the table. And you can see that there are 8 possible outcomes, and these are simple events. And they're simple events because they cannot be they can't be further broken down for this experiment, because our experiment consists of 3 trials, so each one of these is 3 trials. These are the simple events, and they're all equally likely. And so that means that each one has a probability of 1/8. So each of these events has a probability of 1/8. Now, what we're interested in is the number of tails that are showing. So in each of these simple events, we list in the next column how many tails there are. So if there are 3 heads, there are 0 tails. If there are 2 heads, then there are exactly 1 tails. And these are the 3 events that comprise having exactly 1 tails. There are also 3 events that comprise having exactly 2 tails. And there's only 1 event where we have exactly 3 tails. The number of tails is what we are counting, and so the values of the variable x are either 0, 1, 2, or 3. So this column is the first column in our probability distribution. It's the column that gives us the possible values of the random variable. But remember, we had to build that column by thinking about the simple events and determining the number of tails for each of those simple events. Then we look at the probability of each of those events. Well, for that, we can do this a couple of different ways. For having 0 tails, we see that there's only 1 event where there are 0 tails, and that event has a probability of 1/8, and so the probability is 1/8. But when we look at having 3 tails, we see that there are 3 events where there are 3 tails, and each of those events has a probability of 1/8, and so altogether, the total probability of all 3 of those events is 3/8. There's 3 out of 8 ways for that to happen, having exactly 1 tails. Similarly, for having exactly 2 tails, there are 3 events where we have exactly 2 tails, and that's when x is equal to 2. The number of tails is 2. And since there are 3 of those events, and they're equally likely, we have a probability of 3/8. The final event is having exactly 3 tails. There's only 1 way that that can happen, and that event has a probability of 1/8. So it's just a way of recategorizing these events into groups. And those groups, now we have 4 of those groups, each representing the values of the random variable x, and then we can determine the probabilities for each of those events. And now these last 2 columns give us the probability distribution of this random variable. Notice that the probabilities still add up to 1. Okay, this takes us to the definition of a discrete random variable. These 2 previous examples used discrete random variables. Discrete random variables have either a finite number of values or a countable number of values. And so for our purposes, in the previous examples, we had a finite number of values. The first random variable x had 2 possible values. I believe that the values of x in that first example were either 1 or 2. So that's a finite number of possible values. In the second example, x had 4 possible values, 0, 1, 2, or 3. Again, a finite number of possible values. And so if a random variable has a finite number of values, it's a discrete random variable. Discrete data gives rise to a discrete random variable, and continuous data gives rise to a continuous random variable. This third example deals with continuous data because the bulb can burn out at any time. It's not constrained to just a whole number of hours or minutes or whatever you're measuring in. So if the bulb could burn out at say 4 days, and then 5 hours, and then 3 minutes, not a whole number. You could express this as a number of days, if you will, but the idea is that the value can be anywhere on the line, not just falling at a whole number. Discrete data, the values of the variable fall only at whole numbers. For continuous data, the value of the variable can fall at any number on the line, and so it has an infinite number of possible values. Now, we have a convention in our book, which we have to make sure we all understand, that if we have a probability value that's very small, such as this number, that's a very small number, in the tables in your text, those numbers are represented by the symbol 0 plus to indicate that the probability is a small number, but it's still a positive number. So we're not going to identify it as 0 because there's always a chance that a certain event could happen, so the probability shouldn't be exactly equal to 0. So here I have a part of the binomial probability table on this slide so that you can see what that 0 plus looks like. So we'll talk more about the binomial probability table as we progress, but just to see, here's one of those 0 pluses, and that tells us that the probability that the random variable has a certain value, which we'll learn how to read from this table, is a very small positive number. And you'll notice that in this table, all the non-zeros or non-zero plus numbers have 3 digits behind the decimal point. So this number would actually have all zeros for the first 3 decimal places, and then it would be a non-zero number. So we just indicate it in the table as 0 plus. Now, a probability histogram is a graphical display of a probability distribution. So you should become familiar with a process for constructing probability histograms. So here I have a table 5.1, which is a probability distribution, and let's talk about why that is. First of all, we see that each of these individual probabilities in this column is a number between 0 and 1. Secondly, we see that if we add all of these probabilities together, we'll get a number that's actually pretty close to 1. In fact, it might even be exactly 1. And those are the 2 requirements for probability distribution. Each individual probability has to be a number between 0 and 1, and all of the probabilities in the probability column have to add up to 1 to cover the entire probability. So here's how we sketch the probability histogram. We'll put the number of the values of the random variable x are placed on the horizontal, and those values are 0, 1, 2, 3, 4, and 5. So I'm going to try and get those on there pretty nicely. 0, 1, 2, 3, 4, and 5. Those values will be the midpoints of the rectangles that I'm going to draw for each of the probabilities. Now my probabilities extend from the smallest value of 0.001 to the largest value of 0.396. So I'm going to let the vertical go up to let's say we'll go up to 0.5. So we'll say this will be 0.1, this will be 0.2, this will be 0.3. Well, I guess we'll just go up to 0.4. We don't have to go much higher than that. Okay, so now we look at, let me get rid of some of this here. We look at the value and the probability for the value 0. The value 0. Look at that probability. The probability is 0.001. It's very, very small. So we're just going to make a really small rectangle, and we want to have 0 as the you want to have this as the midpoint of the rectangle, and that has to be the midpoint of the next rectangle. So we're going to go a very small rectangle, just like that. That rectangle, the area of that rectangle should be 0.001 because that's representing the probability that the random variable x is equal to 0. Now the probability that the random variable x is equal to 0.015 is a little bit more than that, so at 1, midpoint of 1, I'm going to draw a rectangle that's going to go a little bit higher, and I'm already in trouble because my This stuff is really small here, so but I'll just do that. So that's less than 1 still pretty low. Now, the random variable x has a value of 2 with probability 0.088. So I'll make my rectangle come up a little bit higher, like that. And there's the rectangle that represents. So that area should be 0.008. So that's as high as it should go. If you went all the way across here, you'd be at 0.008. If you went all the way across here, you should be at 0.015. If you went all across here, you should be at 0.001. It's just a little hard to do on this iPad, but you get the idea. The next one, 0.264, that's about halfway between 0.2 and 0.3. So my rectangle, which is centered at 3, is going to go all the way up to about that high, and come across, come down. That rectangle, the area of that rectangle, represents the probability that the random variable x is equal to 3. The next rectangle will extend all the way up to 0.396, which is almost as high as 0.4, so I'll go up to there, and then come down to here like that, and that's the histogram, or the rectangle that represents the probability that the random variable x is equal to 4. And finally, the one for 5 is about 0.237, so I'll go about a little bit less than that one, come down about right here, and there you have the probability histogram for this random variable's distribution. And you can see that it comes up to a peak here, and it swiftly goes off to a tail on that end. So it's not a normal distribution. It's definitely not bell-shaped because it just drops off right here. It's not bell-shaped, not symmetrical. In fact, there is a certain amount of skewness to this. You can see that there is some skewness. But that's how you do a probability histogram. Okay, there are a lot of problems in your text dealing with pea pod colors, and I kind of looked up some pictures for pea pods to find out what green and yellow pea pods look like, and sure enough, I found lots of pictures of pea pods that were green and yellow, and these are the colors of peas that Mendel worked with in his famous genetics experiments, and we studied that a little bit in probability, and so we can look at a table of pea pods and the genes and how that all works biologically. So not to get too specific here, you know that you get a couple of genes from your father and you get a couple of genes from your mother. Actually, you get one. Suppose that you get a gene for green from your father and a gene for green from your mother, then you will have 2 green genes and you will be a green pea pod. If you get a yellow gene from your father and a green gene from your mother, then you will have green pea pod because green is dominant. If you get a yellow gene from your mother, right here, and a green gene from your father, then you will have green pea pod again because green is dominant. And then finally, if you get a yellow from both your mom and your dad, then you will be a yellow pea pod because both of your genes are yellow genes. So the theoretical probability of green offspring, well, there are 3 outcomes in here where there are green offspring and only 1 where there's yellow offspring. So 3 out of 4 we would expect about 3 out of 4, or about 75% of the pea pods to be green if we don't interfere with their genetics at all. So Mendel observed 428 out of 580. And if you do the math on that, 428 out of 580 actually works out to 0.737, which is pretty close to 75%. There are some who think that Mendel doctored his results, but we won't get into that. We'll just say that his observation was pretty close to we would expect theoretically. So let's talk about the probability now of observing 3 or fewer peas with green pods. 3 or fewer. Well, if you're going to observe 3 or fewer, that means that the possible values for the random variable x are 3, 2, 1, and 0. 3 or fewer means any number 3 or less. So we take the probabilities for 3, 2, 1, and 0 and add those together. So we go to the table and add those probabilities together to answer this question. That will give us the probability of 3 or fewer green pods. The next question is, what's the probability of observing at least 2 peas with green pods? At least 2 means 2 or more. So we want to know the probabilities for the random variable x equaling 2, 3, 4, or 5. Now we can get that by adding the probabilities for the random variable x equaling 2, 3, 4, 5. And the reason we can do that is that these events are disjoint. So remember, if two events are disjoint, the probability of A or B is equal to the probability of A plus the probability of B, if A and B are disjoint. Now we know all these events are disjoint because you can't have 3 peas and 2 peas at the same time. 2 greens. If you have 3, then they're all disjoint. They're disjoint events. So even if you have 3, the probability of A or B or C, if A, B, and C are all mutually disjoint events, you can just add those probabilities together. And so that's why we can just add the probabilities in this table together, because these events are disjoint, and so they can't all happen at the same time. One or the other will happen. So that's why we can add them together. These events are disjoint. So to find the probability of at least 2 peas with green pods, we could add these 4 probabilities together. You could also shorten your work a little bit, because by the rule of complements, you know that the entire probability column adds up to 1. So instead of adding those 4 numbers together, you could add these 2 numbers together and subtract from 1. So that would give you another way of figuring out the probability. It's a little bit less work. In fact, when you get to the next question, let me erase some of this stuff to kind of clear it off. When you get to the next question, you see that, in fact, using that complement rule is an easier way to do this problem. So let's look at this one. The probability of observing at most 1 pea with green pods. At most 1 means 1 is the most. Oh, so I suppose it's not this one that I want to do the rule of complements for. Let's see what at most 1 means. At most 1 means 1 is the most, so 1 or 0. That's this probability. Add these together. Okay, that's the complementary event of this probability. So since we figured out this probability in the previous problem, we could just subtract from 1 to get that probability. So that's not so bad. So check that out and make sure that you understand why that works. Now the last one is the one I was getting at. The probability of at least 1 pea with green pods. At least 1 pea with green pods means that you have at least one or more, 2, 3, 4, and 5. You would have to add all 5 of those probabilities together. But you can make this simpler by using the rule of complements. Since you know that the total probability in this column is 1, when you add the probabilities for 1, 2, 3, 4, and 5 together, that should be the same as 1 minus the probability of the complementary event. The complementary event would be that you get 0 peas with green pods. And so instead of adding those 5 numbers together, we can just say, well, this probability is the same as 1 minus 0.001, which is it's 0.999, isn't it? Okay, so the probability of getting at least 1 pea with green pods is actually pretty high. It's actually pretty high. Okay, probability distribution table. Again, you can find the mean of the probability distribution. I know there's a lot on this slide. We'll just go through it a little bit. To find the mean of a probability distribution, this is symbolically what you do, but let me show you actually what you do. To find the mean, all you have to do is take each individual x value, multiply it times its probability value, and then add all those products together. So you can see in this column is where I have x times p of x. And so what we do is we take the x value 0 and multiply it times its probability, and of course we get 0. We take the x value 1 multiplied times its probability, and we get 0.015. Take the next x value 2 multiplied by its probability and get 0.176. Do that for all of the x values. Multiply each one times its probability. Write that number down, or save it in your calculator, and then add all those numbers together. Once you add all those numbers together, you get the mean of your probability distribution. And in this one, the mean is 3.752. Since our original data has 0 digits to the right of the decimal point, we will round to 1 digit to the right of the decimal point. That's the rounding rule for mean. 1 digit more than in the original data. So we'll round 3.752 to 3.8. To find the standard deviation, there are two different formulas, but they both give you the same value. The only thing is that the second version is a little bit easier to calculate, at least that's my opinion. Feel free to use either version, but I show in the table how to set up the table for this version. So what you have to do is take each x value and square it. So notice I have a column where the x values are squared, and then that has to get multiplied by the probability. And so you see, after you square each x value, you multiply times its probability. So then I have a column where I've done that calculation. And then you have to add those things together. So here's what I have. This column is the x squareds. Take each number in that column and multiply times its probability, and you'll get these numbers. Take all those numbers and add them together, and so I get 15.004. And then after you do that, you subtract the square of the mean, which you've already calculated as 3.8. Actually, I used the unrounded value in my calculation, and so finally you see that before I take the square root, it's sigma squared, and then after I take the square root, it's sigma, and that rounds in the same way. It rounds to 1. So the mean number of p's with green pods is 3.8, and the standard deviation is 1p. So, when we are finding the means of our probability distributions, what we do is take our x value for each value of x, multiply times the probability, and then put that number here. Take each value of x, multiply times its probability, put that number here. And continue doing that throughout the entire table. Each x value gets multiplied by its probability, and that number gets put here. Add those all up, and see that you can get, oh, wait a minute, this is really bad. This one's not even a probability distribution, so it doesn't even make sense to do all these calculations. The first thing you should always do is make sure that you have a probability distribution, and look what I found out earlier when I was working on this problem. The sum of these probabilities adds up to 1.132. That is way too much probability. Probability should be very close to 1. You can get 1.001, or you can get 0.999 as your sum because of maybe rounding. But this number, 1.132, is very, very much far from the number 1. It's too much probability if you want to think of it that way. So this is not even a probability distribution, therefore it makes no sense to do any of these calculations. It makes no sense to calculate a mean or a standard deviation. It's not a probability distribution.